Okay, let's go ahead and look at an example from the end of Chapter 9 in your book. So I've pulled problem 68 out of the back, and this is the example we can try together. So for problem 68 here, they tell us some information about the compound diethyl ether, which is kind of an old-timey anesthetic. It's not really used for that purpose anymore just because it's so flammable. We also have anesthetics that just work better in general. But we're told that this compound has a heat of vaporization, so the amount of energy required to take the compound from the liquid phase into the gaseous phase of positive 26.5 kilojoules per mole at its boiling point. How much energy in kilojoules is going to be required to convert 100 milliliters of diethyl ether at its boiling point from the liquid to the vapor if it has a density of 0.7138 grams per milliliter? So what I'm going to let you do is try to think about this problem on your own. So go ahead and pause the video, and we'll come back in a couple of seconds and go over this once you've had the chance to try it yourself. Alright, so having tried this on your own, let's go ahead and look at what we're actually dealing with, which is the vaporization of diethyl ether. And remember, vaporization refers to going from the liquid state to the gaseous state. We don't have a new compound. There's no sort of rearrangement of chemical bonds or anything. Really, this is just a physical change. But we are going from liquid to gas. And remember, vaporization is liquid to gas. Sublimation is solid to gas directly without passing through the liquid phase. And fusion is basically melting, where you go from solid to liquid. But here we're interested in vaporization. And so that reaction there has a enthalpy change of positive 26.5 kilojoules per mole. So what are we going to do with the information we have? Well, that positive 26.5 kilojoules per mole tells us that for every mole of diethyl ether that vaporizes, we're going to need to absorb 26.5 kilojoules of energy from the surroundings. So essentially what we need to do is figure out how much diethyl ether we have, specifically how many moles of that compound that we have. And then we can use the enthalpy as a conversion factor between moles and energy. Now, to get the number of moles, we need to actually figure out what the mass of diethyl ether is that we have. And they don't actually tell us what the mass we have is, but they tell us we have 100 milliliters. And for any liquid substance, if you know both the volume and the density, then we can simply multiply those two things together to get the mass. So we're going to start with the given volume, which is 100 milliliters. I'll go ahead and highlight where all this is coming from. 100 milliliters is the volume of ether that we're starting with. And we're going to convert that into mass. And for that, we're going to need the density, which they provided for us. Volume to mass requires density. You can also use density to go in the other direction, but of course, here we're interested in going from volume to mass. From the mass, we can then figure out how many moles of ether we have, and that's going to depend on the molar mass, and we can figure out what that is because we know what the formula is for our compound. It's going to be the atomic mass of carbon times 4, plus 10 times the atomic mass for hydrogen, plus 1 times the atomic mass for oxygen. And then finally, we're going to use our provided enthalpy change, which is right here for this vaporization, to convert that into energy in kilojoules. So let's go ahead and plug in the actual numbers that we have. So we're starting with our volume, which they told us in the problem is 100 milliliters. We're first going to multiply that by the density in terms of grams per milliliter. And as you can hopefully see, that will cancel out milliliters, leaving us initially here with grams, which we can then take and convert into moles using the molar mass. Now, I haven't shown the calculation here, but we've gone over how to do molar mass before. So if you add everything up, you should get 74.12 grams per mole. Perhaps slightly different in the last 1 or 2 decimal places, depending on how you round. But by multiplying by 1 mole over the molar mass, we can cancel grams, leaving us now with moles. And from here, it's just one more step to convert into energy. And for that, we have the number of kilojoules per mole of energy for the vaporization of ether. So we can cancel out moles when we multiply it by kilojoules divided by moles, and this is going to leave us with 26.5 kilojoules absorbed. So that's the amount of energy that's going to be absorbed from the surroundings to conduct this vaporization. And we can tell that this energy is going to be absorbed because we have an endothermic reaction. In other words, delta H is positive. If delta H had been negative, we had an exothermic reaction, we'd be releasing that energy into the surroundings. But as it is, what we need to do is just multiply together everything you see on your screen, and if you plug all that in, you should get 25.5 kilojoules, and again, that's absorbed energy. So hopefully problem 68 there makes sense. Let's look at another example now, which is going to be problem number 70. So this pertains to an actual chemical reaction where they tell us that the reaction of aluminum metal with chlorine gas produces a lot of energy to the point where it produces a bunch of sparks if you actually conduct this reaction. Of course, the compound formed there is aluminum chloride. That's the ionic compound you'd predict based on the ionic charges those elements take. And what we want to know is how much heat in kilojoules is released if we have 5 grams of aluminum that react with chlorine. Now here we're just told the amount of one of the reactants, and we're going to base our calculations on that. Keep in mind there could be examples where we could be provided with amounts of both reactants, and we'd need to do a limiting reactant calculation to determine which reactant to base all of the results on. But here we're just basing it on 5 grams of aluminum. So what I'll let you do now is pause the video, go ahead and try this example on your own, and then we'll come back and go over it. Alright, hopefully you've had the chance to try this on your own. If we go ahead and sketch out how we're going to figure out this information, we were given a certain mass of aluminum, and we were given the enthalpy change for this reaction, which is negative 1,408.4 kilojoules, and the fact that it's negative means that this is an exothermic reaction. So this enthalpy change is going to allow us to convert between moles and kilojoules, and we want to know how many kilojoules are going to be produced. Now, to convert from mass to moles, all we need is the molar mass for aluminum, which, since it's an element, a monoatomic one at that, all we need is the atomic mass for aluminum, which, if you go look that up on the periodic table, is 26.98 AMU, which means that 1 mole of aluminum will weigh 26.98 grams. So if we set up our numbers, let's go through this step by step. We have 5 grams of aluminum, that just came out of the problem, and we're going to multiply that by 1 mole of aluminum divided by 26.98 grams, because that way grams will cancel, leaving us with moles, which is where we want to be once we are going to then use the enthalpy change for the reaction. Now, in the previous reaction, the vaporization of diethyl ether, we had a situation where we just had 1 mole of diethyl ether on each side of the equation. So the enthalpy change associated with that vaporization reaction was the amount of energy associated with the vaporization of 1 mole of the compound. Now, this example is perhaps a little bit more interesting because notice that this enthalpy change here is associated with 2 aluminums in the reaction. And specifically in this context, that means that when 2 moles of aluminum react, we're going to get negative 1,408.4 kilojoules. So we need to take this coefficient into account when we use our enthalpy change here. So that enthalpy change, 1,408.4 kilojoules released, because it's negative, corresponds to the reaction of 2 moles of aluminum and not just 1. And again, that comes out of the balanced chemical equation. So by multiplying these together, we can now cancel moles of aluminum, and that'll give us kilojoules of energy released. And that's going to be 261 kilojoules released. By using the term released, we're stating that it's an exothermic process, and so we don't use the negative sign if we're specifying that it's released. If we just wanted to know the energy change, then you would need to use a negative sign there.